Now, we have not talked much about we talked about the reaction in the upper zone of the blast furnace in detail and about the kinetics of it, but we did not talk much about the reactions in the lower part of the blast furnace. We talked more about the aerodynamics of it, which is quite important for the smooth operation of the blast furnace. But of course, the reaction is also important. So, now in this one I would be talking a bit about the reaction which are occurring in the lower part of the blast furnace. So, due to the high temperature and a strong reducing atmosphere in this region, all the elements in raw materials are partitioned into slag, metal and gas phases. Hot metal production quality for steel making is of secondary importance than the stability and productivity of the furnace. Remember, a very important statement here. So, because sort of getting a right chemistry of the hot metal is not that important, and also it difficult in the blast furnace to do that. So, the main aim in the blast furnace is the stability and productivity. These are the very important factor in the blast furnace then rather than the chemistry of the metal. Of course, chemistry is important, and one has to try as much as possible to control it, but beyond a certain limit you can't do much in the blast furnace, because it's sort of like a black box which is just a covered container, while the steel making operation is a batch type of operation where you can easily manipulate the operation and can adjust the chemistry of the not only hot metal or the steel. So, that is why in the blast furnace chemistry we try to control as much as possible, but not the utmost way. But the utmost importance is about the stability and operation of the blast furnace. So, figure in the next slide. So, a schematic view of the reactions involved in the lower region of the blast furnace. So, we are starting say after the softening zone. So, melting and the hearth region. So, from the melting zone, as you know, liquid comes out, and liquid is in the form of slag and the iron. So, slag is made of gangue material, calcium oxide, silica and magnesium, these sort of material which are present in the slag is in FeO, and the iron which is quite carburized sort of iron saturated. So, and at the TUR level, because the burning of the coke is occurring. So, from the coke S we get sulfur and SiO. So, silicon is transferred to iron at the TUR level much from the this coke, and some silicon, while iron is descending, it gets transferred, and but sulfur goes to the gaseous phase. From the slag, of course, some silica is already there, and some silica can join from here, coke S, and but due to high temperature, even SiO is formed, which goes with the gas flow and may even go to iron, but it also comes back even to slag. Similarly, magnesium at that temperature get vaporized. So, we are talking at here near the TUR level where temperature is high. Potassium and sodium, they get recirculated, and when it settles down into the hearth, so iron goes to the bottom and slag floats top of the iron. So, then the transfer of these silicon, sulfur, manganese, iron occurs at the interface, or when the iron droplets are travelling through the slag layer, that time the transfer of these species occur. So, we would be talking now mostly about these some of the important reaction, mainly silicon, sulfur, some manganese about it. So, if you look at the blast furnace in the stack region, you have a various form of iron oxides which get reduced into the lower one, and whatever CO2 is formed, that goes into CO. In this cohesive zone, because once the solid comes up to here, mostly you get the boostite in this region. So, CO react with boostite, so iron is produced, and in turn that CO2 again react with carbon, forms CO. And also in the liquid form, because at that temperature FeO also can be in liquid form. So, carbon can react and form iron in a liquid form, and carbon even dissolve into the iron. And the gangue also at that time, if some SiO which is coming out react with CO, form SiO2 and carbon under this condition. In this zone, near the combustion or trapping zone, SiO2 which is there in the slag or in the gangue material react with carbon, form SiO vapor, gaseous product, and CO. And this SiO reacts with the iron and which has the carbon, dissolved carbon into it at high temperature. So, silicon get reduced. So, silicon is absorbed by iron and CO is formed. So, that is how the silicon pickup occurs in this region. And SiO2 from the coke as again goes into SiO, can come here, and this reacts again with the oxygen, so CO2 is formed. And sulfur in the ore combined with the lime and the calcium sulphide which goes into the slag. And at in the Hertz region, manganese oxide can react to carbon, and manganese can go into liquid iron. Similarly, if there is a titanium, that can also reduce and go to the liquid iron, and the phosphorus also goes to liquid iron. So, these are the important reaction which occurs in the lower part of the blast furnace. So, all these element goes to liquid iron that dissolve into this, and this is sort of a brief description of the reaction, important reaction which are occurring in the lower part of the blast furnace. The silicon transfer is one of the most in fact important reactions. So, we will be talking a little bit more about it. So, because historically if you see, we will see here SiO2 comes from coke ash and ore gangue, and since long measure of silicon content in hot metal is related to the thermal state of the earth, which could be that the overall reduction reaction with carbon is highly endothermic and slow. So, historically this silicon reaction has been related with the thermal state of the earth, because it used to be believed this SiO this reduction occurs in the earth region, and most of the silicon get transferred in that. And because this is a very endothermic reaction, and that is the region of the observing or measuring the temperature of the earth liquid and other things. So, thermal state was very important historically, what I am talking, but now it has been found this is not the thing by which silicon get transferred to metal. It is mostly by a gaseous phase, as you can see in this. So, SiO2 SiO gas is generated in the raceway region, which is absorbed react with the carbon in this and absorb silicon get absorbed in the metal, and so that is how the maximum silicon comes, and in fact when it is coming down it reoxidizes, it gives away some of the silicon and which gives the final silicon content. So, SiO2 in slag it gives away actually, and in same thing this SiO also goes to the slag here. So, this is a sort of a cycle we would be discussing a bit now. So, the normal that reaction in the heart region we set with the slag and the carbon gives this is you can say even a dissolved carbon or normal with the metal or normal carbon that gives you the silicon which is dissolved into iron and 2 CO. So, obviously the reaction is quite endothermic this. So, this endothermic nature of the reaction you need temperature in this. So, silicon transfer to the metal also can occur either via slag metal reaction shown above, or the other one is silicon transfer to the metal can occur either via slag metal reaction shown above or via gaseous route. So, this is by slag metal reaction, and this is not possible what a recent study has revealed. But via gaseous route there are two ways. For iron which is free of carbon, this reaction is possible. So, CO2 gas not CO gas. So, SiO plus CO, Si plus CO2, and where the carbon is there in iron, this reaction is possible. So, this goes with the metal and CO. So, carbon in the metal react with the gas form CO, and silicon goes into the metal into iron. So, mostly this is the reaction which is responsible for the silicon transfer in hot metal, because SiO gas is generating in the dropping zone, and liquid iron which is usually quite saturated with carbon. So, that carbon react with SiO gas, ascending SiO gas, and silicon get absorbed into metal, and this we do not have that much gas, usually iron free from carbon, it could be at the upper part which is not possible. So, the rate of this reaction, the reaction which is possible of this third reaction is expressed as follows. So, this is the rate of reaction for this, and this is the rate constant, activity of carbon, and area, cross sectional area or interfacial area. Similarly, and the rate carbon, PaSiO, partial pressure of silicon monoxide. So, this term you put it in that. So, really rate of reaction is directly proportional to the partial pressure of SiO, and this rate constant is given by this expression. But this is again a experimentally measured value and established value, and it is used when your carbon percentage in iron is about 2.8. For saturate 2.8, 2.9, this is sort of in the blast furnace when it is dripping down, but for saturated carbon melt there is a different rate expression which can be found. And now the equation 1, increase in temperature makes delta G more negative. So, if you increase the temperature, therefore, the forward reaction is favored and more pickup of silicon ion. So, in this way this reaction and more, but so SiO2 is reduced, which makes delta G positive and favors the reverse reaction. So, naturally you need a very high temperature, which is not possible in the hot region in that, and this way this reaction silicon transfer through this reaction is not possible in the hot region. Of course, quite a bit SiO2 is combined with the lime, which reduces this or which increases then the basicity, and in that way one can further probably increase the silicon transfer if one look at the kinetics of this reaction. So, it has been now well established that almost all silicon transfer in the hot metal occur via gaseous phase in the dropping zone and near the TUR, and negligible amount of silicon transfer is occurred via slag metal reaction. So, dissection of live and experimental blast furnace gives the clear evidence of it. Now, this is not the only one which has been found through the dissection of live or experimental blast furnace. In fact, it has been also found that so this is a TUR level, coke is surrounded around the raceway. So, even evidence has been found that silicon carbide is formed. So, with the carbon with the coke, even SiO2 can react and can form silicon carbide, and through that even some of the silicon pickup when the hot metal is flowing through that silicon carbide sort of layer, then it can pick up silicon. But of course, the major one is the gaseous phase of silicon monoxide through which the silicon transfer occurs in the hot metal, and these are the result of the experimental blast furnace. So, this distant from the TUR level. So, this is TUR level below and above just 0.5 meters. So, you can imagine that the raceway is also there. So, you can see the silicon content at the just TUR level is very high. So, most of the silicon pickup is occurring SiO paper because it is forming here, and that depends in which radial direction, that is how these points are given. So, most of the SiO paper picks up by falling liquid metal and it absorbs the silicon. So, silicon pickup is quite high. Similarly, in fact, you can see even the manganese pickup at that level is high and not that much phosphorus, but even the titanium is quite high because the temperature at this place is very high. Mostly in the earth region, the equilibrium they try to equilibrate according to the thermodynamics, but most of the pickup is occurring in this region. In fact, this is also another evidence. It is found that temperature near the TUR is like 1900, 2000, 1800, 1700. So, these are the isotherm of the temperature near the TUR region, and this is the silicon content in the hot metal. So, which directly related with the temperature, and as the temperature is higher, SiO formation certainly is quite high. So, in this region one can expect a very high SiO formation, and that which is also indicated by the metal which has been picked up through this zone. So, very high content of silicon, and that is very well established silicon transfer occurring by a gaseous phase. So, in summary, I would say also to reduce the silicon content in hot metal, reduce the temperature, increase the basicity, increase the top pressure, or if you need a really very low silicon content, is not possible through that, then external hot metal desiliconization is necessary, which can be done using mill scale or iron powder injection in either in a torpedo, car, or other outside process. So, in mill scale the reaction would be like this. So, silicon get silicon dissolved silicon form silica, and in by injecting iron powder again it forms silica and metal comes. So, you reduce the silicon content into that. So, these are the way you can control the silicon content, and this is the mechanism.